All right, so I'm going to work this sheet out for you, give you the answers, stumble through it a little bit, we'll see. All right, so let's see. The temperature of a 5-liter container of N2 gas is increased from 20 to 250 degrees. So that's an increase in temperature of what? 230 degrees Celsius. If the volume is held constant, predict qualitatively how this change affects the following. So let's say we have a container, and we'll call it rigid. Okay, that's what that means. And it's 5 liters. That's not going to change. Okay, that's what that means. It says the average kinetic energy of the molecules, which we know is the temperature, right? So we're saying it's increased from 20 to 250, so we're going to say that this one also increases, right? Because, well, it goes from 20 to 250. The root mean square speed of the molecules. Now, root mean square really factors in the other molecules in the air. Right? The air. Combine my words, you know, right? So that's really sort of talking about. So if I make the temperature go up, I still should make the root mean square increase as well. There's how much speed, and we know the temperature is kinetic energy, which we know is 1/2 mv squared. So the velocity goes with speed. The strength of the impact of an average molecule with the container walls. So this is a pressure thing, right? And if we keep the container the same size, but we make the molecules move faster with more energy, then they should collide with the container more and with more force. So I would say the pressure should go up. Now, if I could make the room bigger, maybe not, right? Because that way I could go ahead and have the room expand, right? The total number of collisions of molecules with walls per second, that's definitely an increase. We're moving in the same space, but a lot faster. Okay, 2. Let's see if I can get it on the screen. All right, number 2. Consider 3 identical flasks filled with different gases. Which flask of the molecules has the greatest kinetic energy? All right, so if you look and see, I believe 0, 0, 0. So I think we can say that they all should have the same kinetic energy, because they're all the same temperature. Which flask will the molecules have the greatest velocity? Well, that's based on this equation. So if it's a large molecule, then it moves slower to get the same kinetic energy as a small molecule. It has to move faster. So in this one, if I'm looking for the greatest velocity and this is the same, all I'm really looking at is the masses. So the bigger the mass, the smaller the velocity. The greatest velocity should be small. So this one should be the fastest, H2. Okay, yeah. 3. Indicate which of the following statements regarding the kinetic molecular theory of gases are correct. For those that are false, formulate the correct version of the statement. The average kinetic energy of a collection of gas molecules at a given temperature is proportional to mass square root of the mass. The square root of the mass. Okay, so this first one will be false, because the average KE is proportional to the temperature only. Okay? Gas molecules assume to exert no force attraction. True, because it's acting ideally. Ideally, spelled it wrong, right? That's one of the things, right? They're not attracted to each other. If they were, then they wouldn't be gases. Or wouldn't be gases of all ranges. All right, next one. All molecules of gas at a given temperature have the same kinetic energy. This would be false. Okay, it's a range of temperatures, right? So we saw the diagram where they had the big hill and down, right? And the greater the actual temperature, the smaller the hill, kind of thing on there. So it's all a range of temperatures, right? distribution of kinetic energy. Right? All molecules of gas, the volume of gas is negligible compared to the total volume which the gas contained. Well, that's true. That definitely is a kinetic molecular theory thing, right? And all gas molecules move at the same speed at the same temperature, which we know is false, because we know that Ke equals 1/2 mv squared. Okay? All right. So what we need to do is look at the ideal gas law, PV equals nRT, and recognize that pressure and volume are on the same side of the equation. They're inversely proportional. Oops, I spelled it wrong. Inversely proportional. Okay? When we deal with constant quantities of gases, so N can't really change, right? But in this scenario, we're adding more gas, right? We're adding gas inside of it because he was spilling his tires. So that kind of changes everything. Both pressure and volume can increase when you do that stuff. Okay, so at first, he's just increasing the pressure within the tire, and then, ready, it goes ahead and exerts force on the outside of the container, and it causes the volume to expand. Okay, because they're inverse proportional and you're increasing N, right, they both have to expand. Next one. Ethanol burns in air. Sorry. Ethanol burns in air. To the equation there. We had to balance it first. So we end up with 3, 2, 3. Balance the equation determine the volume of air in liters at 35 degrees Celsius. So this is pressure. That's temperature. So this becomes 308 Kelvin. 227 grams of ethanol. Volume of air in liters. All right, so it gets a little bit tricky. So we're going to get the total pressure and see what we do from there. We'll balance it first. It's balanced. We'll label what we have. Okay, and first things first, we have 227 grams of ethanol. So we'll convert gram of ethanol into moles of ethanol, which ends up being 4.93 moles. Let's just make it S. And then we know that it's a 1, 2, 3 for oxygen because we need the gas, not a liquid. So we'll take the 227 grams of ethanol and convert it into moles of ethanol, which is what we did. And then we'll go between these two, right? 1 to 3. So 4.93, 1 mole of F, every 3 moles of O2 gives us 14.781 moles. No, we don't need that many numbers. 14.8 moles of O2. So then we go ahead and we're going to plug that into PV equals nRT. Solving for P, right? Sorry, solving for V. We'll plug everything in. 14.8 moles times 0.0821 liters times ATM over moles times Kelvin times the temperature, which is 35,308 Kelvin, divided by the pressure, which is 1.04 ATM. Okay, so then we end up with 359.71 or 359 liters, we'll call it, right? All right, so this is the liters of O2 in the air, and we know the air is 21 out of 100, right? So the air volume times that number 21% should give you the oxygen volume. right? Give the oxygen volume. Let's move this back onto the page. That's true. 21 over 100 is the percent of oxygen times the air should give you the individual oxygen volume, right? It's percentage of the air. Then we go ahead and we solve, right? We multiply both sides by 100. So 359 times 100 divided by 21. You end up with 1710 liters. Okay. And the last one, BeC2O4. It's a hydrate. It's broken down into those two parts. When heated 220 degrees Celsius, 3 grams of this. All of that actually. Dehydrates completely as present above. Find the volume of H2O. So you want the liters here. 220, 735. So first things first, add 273, so 493 Kelvin. Sorry, 493 Kelvin, good. And 735 divided by 760. 0.967 ATM, right? And we have 3 grams of this. So we're going to take 3 grams of the BeC2O4 times 3H2O. Okay? So we got to get what this weighs per mole. So we'll do that. 1 mole of BeC2O4 dot 3H2O, it should be 3, right? Is equal to, let's see. 9 plus 24 plus 64, 18 times 30 equals 151. So we're going to convert this over into moles. 1 mole of the substance, 151 grams. So 3 divided by 151 is 1.99 times 10 to the minus 2 mole. And we're going to go from 1 to 3, right? So we have 3 moles of water. All right, 1 mole of the Be, or 3 moles of water. We got that there. 5.96 times 10 to the minus 2 moles of H2O. And then we have all our things. V is equal to P, let's see, nRT over P, right? 5.96 times 10 to the minus 2 moles times 0.0821 liters times ATM over moles times Kelvin, times the temperature, which is 493 Kelvin, divided by the pressure, which is 0.967 ATM. Moles, kelvins, ATMs all cancel out, right? Times 0.0821 times 493 divided by 0.967. 2.49 liters.